Here are the answers to the questions on page 15 and 16 on rotation practice questions. So I'm going to highlight the answers so you can check to see which ones you got right and wrong. And then if you got a question wrong, you just fast forward to this video to where the explanation is for that particular question. So here are the answers. So 1, the correct answer is 2. 2 is 1. 3 is 2. 4 is 2. 5 is 4. 6 is 3. 7 is 4. 8 is 4. That's usually the tricky one. 9 is 4. 10 is 4. Oh my goodness, what's going on here with the world? 11 is 1. 12 is 3. 13 is 3. 14 should be 6 hours. If you're uncertain, so if you're done, if you got all of them right, then you're all done with this video. Nice job. Go on and enjoy the rest of your day. What I'm going to do now is I'm going to go over each one of these individually so you could, if you got one wrong, just fast forward through the video until you see me going over that particular question. So number 1. Doesn't say number 1, does it? First question. The diagram below shows the latitude and longitude grid on the Earth model. And it's asking us, what's the time difference between points A and B? So when we look at this here, we see that A is sitting on the 0 degree longitude line. So A is on this line, which is 0 degrees. So A is on 0 degrees. And B is on this longitude line, 75 degrees. So A is 0, B is on 75. So there's a 75 degree difference between the two. Well, we know that the Earth spins 15 degrees per hour. If the Earth spins 15 degrees per hour, all we have to do is divide this to see how much. It just so happens that on our chart as well, each of these lines is 15 degrees apart. So if I look at this, there's 0. Here's the 15 degree line, the 30 degree line, 45 and 60. So I know that each one of these is an hour. So 1 hour, 2 hours, 3 hours, 4 hours. It's a 5-hour difference. Again, I could do 75 divided by 15 and get 5 hours, or I could actually count 1, 2, 3, 4, 5 hours in between. So 1 is 2. 2, the apparent rising and setting of the sun is viewed from the Earth is caused by. Why do we have night and day? We talked about that in our effects of the Earth notes, that we have night and day because the Earth is spinning, right? What are the effects of the Earth's rotation? We get day and night because of that spinning around. 3, which change would occur if the Earth's rate of rotation were to increase, to spin faster, right? So if the Earth spun faster, what would happen? Well, we know that the Earth spinning is dealing with our day. So it doesn't have anything to do with the year. So I get rid of choice 1, which talks about year. I get rid of choice 3, which talks about year. It's about the day. So notice these questions when they set them up. If I look at the beginning, it just says the answer is either the year or the day. Well, if we're talking about the Earth's rate of rotation, rotation is dealing with the day. So I get rid of 1 and 3. The day is going to get shorter or longer if the Earth spun faster. Well, our day would be shorter because the Earth is going to go around faster. 1 day is going to take less time. So, right, so faster, increasing the rate means it spins faster. Faster means less time. All right, let's take a look at number 4 now. What causes the Coriolis effect? So we had in our notes 3 pieces of evidence that the Earth rotates. Actually, let's do 4 and 5 together. There are 3 pieces of evidence in our notes that the Earth rotates. They were the Coriolis effect, Foucault's pendulum, and star trails. Coriolis effect, Foucault's pendulum, star trails are evidence that the Earth rotates. So if you see anything that mentions the Coriolis effect, if you see anything that mentions Foucault's pendulum, either of those two, they all deal with the spin or the rotation of the Earth. So as soon as you see Coriolis effect, you say, oh, it's about the rotation or spin of the Earth. As soon as I see Foucault's pendulum, spin or rotation of the Earth. Let's take a look at number 6. Which statement best explains the apparent daily motion of the stars around Polaris? So when we look at star trails, these star trails, which make these circles around the middle star Polaris, are caused by the Earth spinning. As a matter of fact, I guess we could have used this here for that question as well. So Coriolis effect, Foucault's pendulum, and star trails, the movement of star trails, are all about the daily motion of the star trails, are all about the Earth's rotation. If something happens every day, it's all about rotation. Number 7, the spinning of the Earth on its axis causes the apparent rising and setting of, what rises and sets? So we all know the sun rises and sets. Most people get this question wrong because they choose choice number 1. But everything is going to appear to rise and set, meaning the moon and the stars and the sun, because the Earth rotates. And they all rise and set, both the sun, the moon, and some stars rise and set 15 degrees per hour. So as you're seeing the sun rise, as you're seeing the moon set, as you're seeing stars rise, it's always 15 degrees an hour because it's not those things that are rising and setting. It's really the Earth that's rotating. Question 8. Earth's rate of rotation is approximately, so a lot of times we put in our notes, we hammer this home, that the Earth's rate of rotation is 15 degrees per hour. That's the number we want you to remember, and that's true. So a lot of times people get this wrong because they see that 15 right there. That's 15 degrees per day. No, the Earth doesn't rotate 15 degrees per day. Notice all of these choices give us per day. How many degrees does the Earth rotate per day? Well, per day, it's rotating 360 degrees per day or per 24 hours. So the correct answer is 4. Yeah, usually people get that messed up. If these said per hour, then the correct answer would be 2. Number 9. Again, as soon as we see Coriolis effect, rotation. 10. We got this map here. I got A and B again. What is the difference in longitude? So how many longitude differences there from A to B? And they tell us that there's a 4-hour time difference. Well, I know the Earth spins 15 degrees per hour. So that means in 1 hour, there would be a 15-degree difference. In 2 hours, there would be a 30-degree difference. In 3 hours, there would be a 45-degree difference. And in 4 hours, we get a 60-degree difference. We just keep adding 15 degrees. And it just so happens on this diagram that the longitude lines they have drawn for us are 15 degrees wide. Notice 1, 2, 3, 4 hours. So 1, 2, 3, 4 hours between. So this is 15 degrees. This is 15 degrees. This is 15. This is 15 for a grand total of 60 degrees. 11. The diagram shows the Earth is viewed from above, so we know that the rotation is counterclockwise. What is the time at location B? One of the things that I like to do here is if the sun is shining from here, I could draw the line that separates night from day. So there's nighttime. Here's my daytime. We could also shade that in if you'd like. So I notice that B is not at nighttime and it's not at daytime. It's right on the border. So that's got to be one of those either 6 a.m.s or 6 p.m.s. And then I just got to look at the rotation. If the Earth is rotating this way, when you go from nighttime to daytime, going from night to day happens in the morning, 6 a.m. Down here would be 6 p.m. Down there because we're going into nighttime. Number 12. As soon as you see Foucault's pendulum, as soon as you see anything about Foucault's pendulum, you know it's talking about the rotation of the Earth or the Earth spinning. 13. The diagram represents the direction of the Earth's rotation. So notice we have a very similar diagram. They shade nighttime for you. Notice that it's switched. Now the sun is coming from the other direction. It's switched on there. What time is it at point X? We know that point X is, it's not noon, it's midnight. Sorry about that. Midnight, there we go. That's in the middle of the night, therefore midnight. Sorry about that. 14. A camera was placed in an open sky. You can see these star trails. They show us that the star trails are 90 degrees. That's got to be 6 hours because you know a 1 hour photograph is going to leave behind a 15-degree star trail. A 2 hour photograph is going to leave behind a 30-degree star trail. A 3 hour photograph is going to leave behind a 45-degree star trail, right? Every hour is another 15 degrees. If we go to 6 hours, that's going to equal a 90-degree star trail. So 90 degrees would give us 6 hours.